All right, so this is our review lecture on projectile motion. So we have been looking at how to add and subtract vectors. This is to enable us to analyze the motion of an object that's moving in two directions at the same time. But this time we are looking at an object that's moving horizontally relative to the ground and vertically, so in the air. So things like someone skating off of a stairwell, or someone kicking a ball or throwing a ball, like these little animations here. Okay, so in class we hypothesized what we would thought would happen when we had one marble that was dropped and another marble that was horizontally launched, and they both started off the same height off the ground. And so we discussed what you thought would happen. Most people said that the marble that was dropped would hit the ground before the marble that was horizontally launched. Very few people said the horizontally launched marble would hit the ground first. And a small minority of students said that they thought that both marbles would hit the ground at the same time. And when we tested it, we found out that, in fact, both marbles hit the ground at the same time. Why did that happen? Well, we're going to look at it in our next unit, but you have a marble that is just dropped and released from rest, and its initial velocity in the y direction is 0. And then you have I'm going to color that in, and then you have another marble that is launched, but it's launched with the initial x velocity, which is greater than 0, but the y velocity is equal to 0. So both marbles, they fall to the same part of the ground. And so even though it's got this horizontal velocity, the vertical velocity of each of them is the same, and they both drop from the same height. And if you remember in our analyzing motion of a falling object, when we look at the GPS equation, so I'm just going to do delta y equals 1/2 gt squared plus VIY times t, that's how we're going to figure out how long it takes something to fall to the ground. So if they both fall the same height h, and they both have the same acceleration, 10 meters per second squared, and they both have the same initial y velocity, which is 0, then when we solve this, we're going to get the same time. So they both hit the ground at the same time, whether it's horizontally launched or if it's dropped from free fall. So when we look at projectile motion, I'm going to clear this off so it's not distracting anymore. We're talking about motion moving in the vertical and horizontal, so dimensions, same dimension simultaneously. And so what's interesting to note is the position, the vertical position of an object that's dropped from free fall, or thrown up and then comes back down, or thrown at an angle and comes back down. You'll notice that the vertical positions of the object at specific moments in time, the same moments in time, are the same. So regardless of if the object is moving horizontally or not, when it moves through the air, the vertical positions are going to be the same. This is on the way up, and on the way back down is the same, whether it's thrown straight up or straight down, thrown at an angle, or dropped horizontally. And that has to do with the fact that the only force acting on it is the force of gravity, which gives it that negative 10 meters per second squared acceleration. And so here's another animation of what we did in class. Was an animation of what we did in class. So instead of two marbles being dropped at the same time, this person's throwing a ball, and then this object is dropping a ball. And so the motion of a falling object where we ignore air resistance and it's moving horizontally is called projectile motion. So horizontally, the object is moving at constant velocity. And that's what this diagram here is. If there was no gravity, horizontally, the object would be moving at constant velocity, because for the same amount of time, it's changed the same position. But if vertically, it's accelerating, meaning it's speeding up as it moves towards the ground. So when you combine those two motions, then you should get this sort of parabolic motion, which combines the horizontal constant velocity motion and the vertical constant acceleration motion. So it's super important whether we're talking about a ball moving through the air, a boat moving across a river or in the ocean, that if there any object that's moving horizontally and vertically at the same time, or in two dimensions at the same time, that you're going to treat that horizontal motion separate from the vertical motion. Go back and look at the boat crossing the river problem from the previous video if you want to review that. Okay, so in class you had a notes template that you would be filling out, similar to what we did in Unit 2, a tip sheet. And so I just want to draw your attention to these problems tend to be like the last unit's problems with falling objects, and it feels like we're only getting like a little tiny bit of information, like 1 or 2 numbers related to this problem. But in fact, there's a lot of things we already know to be true just from the type of motion we're observing. So anytime you horizontally launch, like in this animation, there's a cannon ball being launched by the cannon. And so if we were to analyze this motion here horizontally, it's going to have initial velocity that's not equal to 0. What that initial velocity is depends on the scenario, but it's often given, or maybe we have to solve for it. But it's going to have an acceleration of 0 because it's moving horizontally with a constant velocity. So as you look at this animation, once the cannon stops pushing on the ball horizontally, then there's no other force, nothing pushing or pulling it horizontally to cause it to change its horizontal motion. And so next unit we're going to say, well, there's no other force, especially because we're ignoring air resistance. So if the acceleration is 0, that means the initial velocity and the final velocity are the same, hence the constant velocity notion. Vertically, though, we're looking at just the object falling, right? So initial velocity, if it's horizontally launched, there's no vertical component of velocity, so the initial velocity is 0 meters per second. It's falling through the air, so the acceleration is negative 10 meters per second squared. And just like the last unit, how much time the ball spends moving depends on the amount of time that it spends falling, which depends on the height of the drop. So vertically, the object is going to be constantly accelerating or in free fall. Oh yeah, I forgot. So I like to give these kinds of problems a nickname. It's called, uh-oh, where did the cliff go? And so we have our same equations of motion, the GPS equation and the speedometer equation. And the vertical motion aspect of projectile motion, it looks the same as it did last unit. The position of an object in the vertical direction is equal to 1/2 the acceleration times time squared plus the initial velocity in the vertical direction times time plus the initial position. So this is the GPS equation, which helps us determine where an object is at a specific moment in time. Because in the horizontal direction, it's moving at a constant velocity, the acceleration is 0, so that part goes away. So this is still the GPS equation, but this is the GPS equation that we first learned in Unit 1, where there is no acceleration. And then this is the speedometer equation we learned in Unit 1, where the velocity is constant, so the velocity just depends on change in position over change in time. But in the vertical direction, it is accelerating, so this is our most recent version of the speedometer equation, where I can figure out the instantaneous velocity, which is how fast and what direction an object is going at a specific moment in time. What moment in time? Whatever time I'm plugging into this equation here. Okay, and so here's another example of projectile motion. We've got a plane that's dropping some supplies, and because the plane has an initial horizontal velocity, so does the package that is dropping, and so it's going to be moving vertically and horizontally at the same time. Okay, so here are the other things, the important ideas to remember for this kind of motion. Again, I'm going to repeat what we said earlier. In the horizontal direction, the object moves with a constant velocity. In the vertical direction, the object is accelerating. The time that the object is moving horizontally is exactly the same amount of time it's moving vertically. The time that an object falls through the air depends on the height of the drop. And the horizontal distance traveled by that object depends on the time in the air and the horizontal velocity. So if it fell from a bigger height than this, then it would be increase in time. If there were a greater horizontal velocity here, then it would have a greater displacement in the horizontal direction. Okay, and now we need to look at the graphs of motion, which we've already seen these before. On the left-hand side, we're looking at the horizontal position versus time, horizontal velocity versus time, and horizontal acceleration versus time. And these graphs are exactly the same graphs we saw in Unit 1. Constant velocity, and if the velocity is constant, the acceleration is 0. On the right-hand side, we have the vertical equation, graphs of motion, and this is position versus time. Oh, my time axis got cut off here. But position versus time, velocity versus time and acceleration versus time. As you can see, the slope is increasing in the negative direction. So this is speeding up in the negative direction, which is why our velocity versus time graph shows speeding up in the negative direction. And since this is speeding up in the negative direction, we have a negative acceleration. And so these graphs match. Okay, so now we're going to do a sample problem. And so this is a typical B-level kinds of question where we're horizontally launching something off a vertical height with a vertical height here. So I'm going to use those same problem. I'm going to squeeze this down here just a little bit. Make it, oops, sorry. Let's go this way. A little bit smaller here. Okay, and then I'll make this a little bit wider here so I can fit more. So I'm going to leave the problem on the left-hand side, and I'm going to use the iPad screen to show you how I work through the problem. Now, we're going to solve this problem in much the same way we've solved previous problems. It's going to require a KU-EQ table, but now my KU-EQ table is going to have a second layer of information here. I'm going to separate my horizontal motion from my vertical motion. And so I'm still going to have knowns, unknowns, and equations, but I'm also going to separate it now into horizontal and vertical information. Okay, so I'm just going to draw a line here, and then this is going to be my vertical information, and this is going to be my horizontal information. It doesn't matter what order you put that in. And so now when I read through the problem, I'm going to have to make a decision, not only like what kind of information am I getting, but also, is it horizontal information? Is it vertical information? So we're going to read through the text right now. And it says here, a skateboarder is trying to skate horizontally off a building and jump over a pool as shown. Oh, there's a typo there. I'll have to fix that. The roof of the building is 27 meters above where he will land. The skateboarder is moving 15 meters per second. Neglect air resistance. A, how far away from the building do they land? And B, what is the velocity of the skateboarder, excuse me, the instant before they land? Oh, the instant before they landed. Okay, so how fast are they going? So first off, I see here that the roof of the building is 27 meters above. So then this distance from here to about here, that vertical distance, you can say initial position is 27 meters and final position is 0 meters. Or you can even be simpler and say, or delta y is equal to negative 27 meters. Why did I put negative? Remember, the object is moving in the negative direction, so its displacement is negative, hence the negative 27 meters. Okay? Now I see another number. The skateboarder is moving 15 meters per second, and according to the diagram, he's moving horizontally at 15 meters per second. So I know the initial velocity in the x direction is 15 meters per second. Okay, so that's all the numbers they're giving us, and they're asking us to figure out how far away from the building. So they want us to figure out this horizontal distance that it travels. So I need to know delta x. And then it says, what is the velocity of the skateboarder the instant before they landed? If they're moving horizontally and vertically, that means they're going to have a horizontal component to velocity. We don't know what that is yet. Oh, we kind of do. And then there's a vertical component to the velocity here. We also don't know the time that he spends moving through the air. And remember, though, the time that we find that he moves vertically is the same amount of time that he's moving horizontally. Okay? So, again, there's still other information that we know that isn't explicitly stated in the problem, just like the previous unit when we had free fall. So if you can see, if you can ignore that this object is moving horizontally, he's basically just in free fall. And if we just drop from the height there, then I know that my initial velocity in the y direction is 0 meters per second. And it's falling through the air, so acceleration is equal to g, which is equal to negative 10 meters per second squared. Okay? In the horizontal direction, it's moving at constant velocity, so acceleration is 0 meters per second, and final velocity in the x is still 15 meters per second, because the velocity is constant, it's not changing. Okay? Those are all the things we know, and the equations that we know how to use is, I'm going to use the delta y, the GPS equation, 1/2 gt squared plus VIY times t. And then we also know the speedometer equation. V final in the y is equal to g times t plus V initial in the y. And then for the horizontal motion, we know that the change in position is equal to 1/2 AT squared plus VIX times t. And the velocity isn't changing, so there's no need for a speedometer equation. Okay, how far away from the building do they land? What is the velocity of the skateboard the instant they have landed? So for part A, I need to know how far away they land, and we said acceleration is 0. So then this equation simplifies. This becomes now delta x is equal to VIX times time. So in order to solve for delta x equals, that's what we're trying to solve for, I need to know the time. But as we said earlier, the time that they spend falling through the air depends on the height. So I'm going to need time from vertical information. So I'm going to use the vertical information to solve for time. So I'm going to use this equation here because I know change in position, I know acceleration, I know initial velocity, and so all I have to do is solve for time there. So that's why I'm going to use that GPS equation in the vertical direction. So delta y equals 1/2 gt squared plus initial velocity in the y times time. So the change in position we've already determined to be this negative 27 meters. So negative 27 equals, now I'm going to enter the gravitational acceleration, which is negative 10 meters per second squared. Time is what we don't know. And then initial velocity in the vertical is 0, so this is plus 0. So now basically I'm going to solve this equation for t. So I'm going to divide both sides by negative 5 meters over second squared. Negative 5 meters over second squared. And so then I get t is equal to 27 divided by 5, because the negative signs cancel. And I'm going to take the square root of that answer. And I get 2.32 seconds. So that's how much time he spends falling through the air. And then remember, I'm going to use this equation here to solve for distance. So then I'm going to say delta x now equals the horizontal velocity times time. And so that equals, the horizontal velocity is 15 meters per second. And the time that we just solved for is 2.32 seconds. And so the change in position horizontally is 15 times 2.32 gives me 34.8 meters. So that's what this distance here is, this horizontal distance. And then what is the velocity of the skateboarder before they land? So I'm going to draw a quick picture here. So we know that he's moving at a constant velocity horizontally. So this is the horizontal velocity. And that he's speeding up so that he's going to have a final velocity that's going to be bigger than what it was before, which was 0. And so I need to figure out what this final velocity is. So v final in the y, and this is v final in the x, but it's the same. And so now I have these two vectors that I have to add together to get my resultant vector, which is v final, and then this is the angle theta because I'm measuring it from the horizontal. So I need to figure out VFX. Well, it's moving at constant velocity, so I already know that the final velocity in the x direction is the same 15 meters per second. But the final velocity in the y direction depends on how long it was falling for. And so this is VFY is equal to g times t plus initial velocity in the y, which was 0. But now we already know how long it's been falling. So g is negative 10 meters over second squared times 2.32 seconds. So then my final velocity in the y direction is a negative 23.2 meters per second. Okay, So now I have the two sides of my right triangle. So then I'm going to use the Pythagorean theorem to solve for the length of this vector here and the angle. I'll use trigonometry, okay, or right triangle geometry. So my final velocity is equal to the square root of VFX squared plus VFY squared. Oops, that went a little crazy there. Okay, so now I'm just going to plug in my numbers. Square root of 15 squared plus negative 23.2 squared. And so I'm just going to plug those into my calculator. Boop, boop, boop. 15 squared plus 23.2 squared. I'm going to take the square root of 763.24. And the answer is 27.6. So 27.6 meters per second. But wait, there's more. I'm not done. I have to give an angle. So I'm going to squeeze my angle over here. So remember, my favorite trig function is tangent. So I'm going to go theta is equal to the inverse tangent of VFY over VX, FX. And so this is now theta is equal to the tangent inverse of 23.2 divided by, in the x is, oh, it's the same in the x, right? It is 15 meters per second. So then that means that theta equals, so I'm going to do 23.2 divided by 15 gives me 1.546666, repeating the inverse tangent on my calculator button. And so I get that this is an angle of 57 degrees. So then the answer is 27.6 meters per second at 57 degrees south of east. Now remember, south of east means I start from the horizontal axis, which we're calling east, and move south, and that's that angle 57. Okay? All right, there's a horizontally launched example. This is a B-level kind of question. I will record a second video on the A-level kind of question, which is the launched at an angle. And either it's launched at an angle and lands on the ground, or it's launched at an angle and lands at a different height. Oh, that's going to be fun. All right, I will talk to you guys soon. Bye.